Hello friends, welcome to the mathematical room. I am the caretaker. So today we are going to start real analysis. So let's start with the question, what is analysis? In analysis we are mainly concerned about these objects, real numbers, sequences and series of real numbers, and real valued functions. Okay, so real analysis is the study of such objects and some aspects about these objects. Like, for example, when it comes to real numbers, we need to know what real numbers are. When it comes to sequences and series of real numbers, we need to know whether they are convergent or not and to what value they are converging. And when it comes to functions, there are several things. For example, we can try to find the limit of a function at some given point, or we can try to know whether a function is continuous, differentiable, integrable, etc. So these things are studied in real analysis. Now, as such, real analysis is distinct from some other parts of analysis, but is related, or at the same time is also related to them. And some of them are complex analysis, which studies complex valued functions. Here we study real valued functions, there we study complex valued functions. The study is somewhat similar, but there are some points which are entirely different. Harmonic analysis, where we study harmonics or waves and how they synthesize some particular functions via the Fourier transform. We study things like that in harmonic analysis. Functional analysis, where instead of studying some particular functions, we are more concerned about the collective behavior of a collection of functions, the overall behavior, how they behave together, and how they form things like topological vector spaces. So such things are studied in functional analysis. At one point we will get to these subjects also. But for now, we concentrate on these objects. Okay? And this is the starting, because real analysis is always the start. Once we have studied all these things, we can then move on to the other parts of analysis, and we will. Now, real analysis is actually nothing but calculus. But there is a very big difference. What calculus is, in calculus also we deal with these objects. We deal with their differentiation of real valued functions, their integrals, etc. But calculus is the collection of computational methods and algorithms needed to deal with these objects. And there we are more concerned about how to calculate or how to find the value of an integral. Say you are given this indefinite integral. Okay. From your calculus courses, you already know you have to make a substitution, take the variable x square and to be some other variable, then with the help of that substitution you can carry out this indefinite integration. So that what you have to do, how you have to calculate, that part is studied in calculus. It's the how part. The why part is real analysis. Whatever questions, whatever techniques you are applying, why are they applicable? So that part is real analysis. So real analysis is the foundation of calculus. So it lets you know why something is true, why a particular formula that you are using in calculus that is true, and also what is the range of applicability of that formula. If you start applying formulas from calculus blindly, then that will lead to some serious problems. So that is one reason we study real analysis, but I am coming to that later. Let us first of all see some of the problems that we are concerned with in real analysis. These are the objects, of course, and I have already said what we study about these objects, but since I am following Terence Tau's book, so I don't want to miss any of his words. So let me just read what I have written from there. Although this does not look good, but I don't want to miss any of his works. If you don't know who Terence Tao is, please look up. You will know who I am talking about. Okay, so these are some of the questions that we are concerned about in real analysis. What is a real number? Now, when we ask what is a real number, it's not a vague answer like this. A real number is either a rational number or an irrational number. That is a very bad answer, okay? In fact, that is not an answer at all. We have to really define what a real number is. Is there a largest real number? After 0, what is the next real number? You see, if you look on the real line, you have a point which represents the number 0. Just next to that point on the right side, is there a number just next to 0? What is the next number? Can we cut a number into infinitely many pieces? That is, if we are given a real number, can we divide it into infinitely many pieces without ever reaching a piece of size 0? Why does 2 have a square root but minus 2 does not? You see, we have square root of root 2, but in the context of real analysis, we don't have anything like this. Why? So it's that why part that we are concerned about here. Why does the set of real numbers look bigger than the set of rational numbers? If so, if that is the case, in what sense is this bigger? Okay, this symbol does not mean your ordinary ordered relation between numbers, but this is something just to convey the largeness of R as compared to Q. Okay, in what sense exactly is R greater than Q? And we have to pin down the actual thing. Okay, so that's what we do in real analysis. So these are some of the questions we will be answering regarding real numbers. Then comes real numbers. Then comes sequences and series of real numbers. Here, of course, we can ask, when is a sequence of real numbers convergent? If we can say stop the terms of a sequence from escaping to infinity, does that mean eventually the terms will settle down and they will make the sequence converge? That is another question. Then, if we have a series of real numbers, that is, if we take infinitely many real numbers, add them up, can we get a finite real number as the sum? That is, can we add infinitely many real numbers to get a finite real number as its sum? Then, can we add infinitely many rational numbers to get an irrational number as the sum of the series? So that type of questions are considered which involve sequences and series of real numbers. When we come to real valued functions, we can then of course ask how to take the limit of a real valued function, or we can ask whether a real valued function is continuous, differentiable, integrable, or bounded. And say we have a real valued function fx, and it takes the value 3 at 0, and it takes the value 5 at 1. If you draw the graph of the function, at 0 the value is 3 say, and at 1 it is 5. If we put the marks like this, 5, then when x lies between 0 and 1, is it necessary that, so this is 3, this is 5, is it necessary that the function will take all the values between 3 and 5? That is another very important question. All the intermediate values between 3 and 5. If so, in what condition, or is it always the case? So these are some of the problems that we are concerned about in real analysis. Now, although real analysis is actually calculus, but as I have said just now, if we don't know why the formulas that we are using are true and what is the range of applicability of those formulas in calculus, then that may lead us to some serious problems. So we will now explore some examples to see what can go wrong if we blindly use formulas from calculus. So this is where the examples come, and since I am following the text of tau, so I will maintain the actual example numbers so that we can refer them back when we need them. So let's consider example 1, 2, 1. So that was actually the first section of the first chapter, 1, 1 of Tau's analysis 1. Okay, there is an analysis 2 also where we study further things. We will do that here. So this is the first section of the first chapter, what is analysis. Then in the next section, 1.2, we see why we need analysis, why we bother to move from calculus to a much harder theory of real analysis. So first example is somewhat, I have already talked about it many times. Division by 0. Okay, division by 0 cannot be meaningfully defined in mathematics, and it can lead to, if you still insist on dividing by 0, it can lead to the destruction of some of the very useful rules that we always use. Say we have something like this, A, B and C are 3 numbers, and we have AB is equal to AC. Then there is a cancellation law which says that you can cancel A from both sides and write B is equal to C. But there is a caveat, A has to be non-zero. If you forget that, then you can get nonsensical results like this. 0 times 1 is 0, 0 times 2 is also 0. Now if you cancel 0 from both sides, then you get this absurdity that 1 is equal to 2. So if division by 0 is allowed, then cancellation law breaks down. Many other things break down, but this is one of the first consequences that we have. So division by 0 is not possible. Then we look at example 1, 2, here this involves divergent series. Okay, we have come across geometric series which looks like this, infinite series of course. And we also know how to find the sum. There is a formula, but forget the formula for now. We multiply both sides by 2. So we get 2s is equal to, so what do we get here? 2 plus 1 plus 1 by 2 plus 1 by 4, etc. You can see that this part is actually again s. So this gives us 2s is equal to 2 plus s, or this implies s is equal to 2. So that's how we find the sum of a geometric series like this. Now if someone has forgotten about the condition that also must be met to find this sum, then he or she may try something like this. Suppose there is a sum. This is also a geometric series, and the person forgets about convergence, or rather the condition under which this series is convergent, or suppose they don't know at all anything about convergence. They just know that whenever something like this is given, they have to find the answer, engineering style. Same thing they can do, multiply both sides by 2. 2s is equal to 2 plus 4 plus 8 plus, this will become 16, but we don't bother to write. And this becomes, you see we are short of 1. So we can add 1 and subtract 1. Minus 1. So this becomes s minus 1. So 2s minus s gives us minus 1. Now the person may feel that although they have found the sum, but it seems wrong. A series all of whose terms are positive, the sum turns out to be negative. But if they don't know about convergence, they will not be able to distinguish between these two results, which one is correct and which one is not. Although, in all fairness, they will somehow believe that this is true, but here something feels off about this calculation. Or even a more confusing series may be this alternating series, 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus etc. It goes like that. The signs alternate. Now to find the value of this sum, one may proceed like this: 1 minus 1 minus 1 plus 1 minus 1 etc. So from the second term onwards, we have taken minus 1 common. So this again is s. So this gives me 2s is equal to 1, or s is equal to 1 by 2. But since now we don't care about anything, and we are just calculating the way we like, without having any care for applicability of these formulas, or the question whether what we are doing is really logical or not, we can do anything. You see, with the same sum, I can arrange the terms like this: 1 minus 1 plus 1 minus 1 plus 1 minus 1, etc. So this gives me that this gives me the result that this sum is 0. Or I can do something else also. I can decide to rearrange or regroup the terms like this. Then my sum will become 1. Now, unlike the previous one, this one, where the sum comes out to be -1, here of course the person will think that something is wrong because 3 different sums are coming. But how will they decide which one is correct, or is there any correct calculation at all? Definitely S cannot be 1 by 2, at the same time 0, at the same time 1, and who knows what else. So what is wrong here? In these cases, we seem to know what is wrong. I mean, at least the ones among us who know about these things. So let's now move on to the next example. Divergent sequences. Okay, divergent sequences. So let x be a real number and L be this limit. X to the power n is a sequence. As n changes, n of course changes from 1 to infinity. When we say 1 to infinity, we don't mean n is equal to infinity ever. It means that the value of n is increasing and it's taking positive integral values. First n takes the value 1, then 2, then 3, and so on. Okay, generating this sequence x squared, x cubed, x to the power 4, and so on. This is the sequence. Now we are considering L to be the limit of this sequence. Note that I am not bothered about whether this limit exists or not. For me, since a sequence exists, there is a limit. Okay. That's why I said engineering style. If there is a question, there must be an answer. No matter how you find that answer, that path does not matter. So I assume that L is the limit. Now I make the substitution. In place of n, I am writing m plus 1. M is another variable which is nothing but n minus 1. So with this substitution, what do I get? L is equal to limit m plus 1 tends to infinity x to the power m plus 1. Now if m plus 1 tends to infinity, m also should tend to infinity, because otherwise m plus 1, how can it go to infinity? M tends to infinity, and this can be written as x times x to the power m. So continuing this godforsaken calculation, I get L is equal to, I can take x outside and write limit m tends to infinity x to the power m. Now this limit, whether I write the variable as n or m, it does not matter. The value matters. So this again is L. So we now have L times, or L minus Lx is equal to 0. L times 1 minus x is equal to 0. So this tells me that either L is equal to 0 or 1 is equal to x. This I can rule out quite easily. Just take x to be not 1. So if I am choosing x to also not be equal to 1, then I must have L is equal to 0. So it seems that I have shown this. Limit n tends to infinity, x to the power n is equal to 0 for all real numbers x not equal to 1. It seems like that. But then for some particular value of x, okay, let's just take x equal to 2. For this value, we get the sequence 2, 4, 8, 16, because we have powers of 2. 2, 2 square, 2 cube, 2 to the power 4 and so on, 32. This sequence is converging to 0. Okay. Or, for example, if I take x equal to minus 1, then I will have minus 1 to the power 1 minus 1. Then minus 1 whole square 1, minus 1 cube minus 1, then again 1. This sequence is also converging to 0. It seems like there is something wrong with these results, but we don't know. Okay, we cannot determine what is wrong with these things, because in the beginning itself we have done something wrong, which I won't point out, but we will come back to these things when we have the knowledge. Right now, let us assume that we don't know and we are blindly applying calculus. Whatever laws we have come across, say for example, if we have a term of which we are taking limit, in that if we have something that does not depend on this variable, then it can be taken out. So that's what we have applied here, and we are just blindly applying calculus and we are getting nonsense. Next, as we go further down this path of examples, we will see that things will become less and less obvious. Till now, things are somewhat okay. I mean, we can recognize what our faults are, but soon we will lose that ability. Example 1, 2, 4. Okay, now this one involves limiting values of functions. So I considered this limit x tends to infinity sin x. Okay, I considered this limit and I assume that this limit exists. Now here also what I do, in place of x I take a variable. What is that variable? I am writing pi plus y for x. In other words, I am defining a new variable y, which is x minus pi. Okay, and I am applying that here. So this limit will become limit pi plus y tends to infinity sin pi plus y. Now as pi plus y approaches infinity, since pi is a finite number, y must approach infinity. So limit y tends to infinity. Now here if you apply your sin a plus b formula, you will get sin pi cos y plus cos pi sin y. That means minus sin y That's what you get. So you can take minus 1 common out. I mean minus 1 can be taken outside of the limit sine y. This is nothing but, if you think of this as L, this is nothing but minus L. We are just calling the variable x by another name y. So this gives me 2L equal to 0 or L is equal to 0. So it seems that this limit is 0. Limit of sin x as x approaches infinity is 0. Now we make another substitution. And what is that substitution? Suppose we now take x equal to pi by 2 plus z. Another variable we are defining z, which is x minus pi by 2. We make the substitution pi by 2 plus z approaches infinity, sin pi by 2 plus z is equal to z. Note that unlike the previous case, we now have a value for L. So this is equal to 0. So because pi by 2 is finite, same like before, z has to approach infinity. Now here if we apply sin a plus b formula, sin pi by 2 cos z plus cos pi by 2 sin z. Cos pi by 2 is 0, so the first term survives, where sin pi by 2 becomes 1. So cos z is equal to 0. Now if we want, we can change this variable name. We are calling it z, we can call it x also. Limit cos x as x approaches infinity is equal to 0. Now we can use these two strange looking equations together to create a nonsense. This one and this one. You see, limit x tends to infinity, sin square x plus cos square x. What is sin square x plus cos square x? 1. Always, for every x, this quantity is 1. So that means the limit is also 1. This is equal to limit x tends to infinity 1 is equal to 1. Now if we use the formulas for limit, limit can be taken inside. Limit sin x, x tends to infinity, square plus limit cos x, x tends to infinity, square is equal to 1. Now these two values are 0. So 0 square plus 0 square is equal to 1. That means 0 is equal to 1. So this is one nonsense. This is one absurdity. What went wrong, okay, in this calculation? That we have to clarify later on. Let's now move on to the second one, the next example. Right. Consider a finite array of numbers or a matrix like this: 1, 2, 3, 4, 5, 6, 7, 8. In fact, is it this exact? Yeah. Yes. Because I have to be careful about these numbers. Okay, this is a finite matrix. Now, before you, we are not concerned about the fact that this is a matrix or anything. Just think of this as a square arrangement of numbers. This arrangement has some rows, 3 rows and 3 columns. What happens if we add the numbers in the first row? What do we get? 6. If we add the numbers in the second row, we get 15. Add the numbers in the third row,